All right, so next up we are looking at multiplying radicals, okay? So first of all, the first things you need to know is that they have to have the same index number, okay? If the index numbers are different, the little numbers inside the check marks, if those are different, then you can't multiply them together, okay? Also, when you multiply, the index number stays the same, okay? So your index number is not going to change. But as you kind of take note up here, you notice that we have two expressions. They have the same index number. The answer has the same index number. And you basically just multiply the radicands together. Okay, so it's very similar to what we did with square roots. So this guy right here, I can start by simplifying this. It's still going to be a cube root. 5 times 50 is 250. And then from there, we're just going to simplify this like normal. So you're either going to look for a perfect cube that evenly goes into this one, or you can birthday cake it. I happen to know that 125 is a perfect cube, so I can break this into the cube root of 125 times the cube root of 2. So that's 5 times the cube root of 2. Okay? All right, this next guy here, so when I multiply these together, the 2 and the 3 multiply to the 6, and then I've got the fourth root. 8 times 4 is 32. Okay, and then I want to see if I can simplify that at all. So let's see, I'll do birthday cake method for this one just to change it up. So 2 goes into that 16 times, 2 goes into that 8 times, 2 goes into that 4 times, 2 goes into that twice, 2 goes into that once. I'm looking for a set of 4, so there they are. So I'm going to have a 2 on the outside and a 2 left over on the inside. And then this 6 that was in front the whole time, you just multiply those together. So it's 12 times the fourth root of 2. All right, no big deal. All right, so then this next guy here, this one is going to be like a distributive property. Again, the index numbers have to be the same. You can't add these two together because they have different radicands, and it doesn't work that way. But I can multiply, so I can distribute here. So this is going to become the cube root of 12 plus the cube root of 24. Okay, and if I try to simplify that, let's see, 12 is 2 times 2 times 3. There's no sets of 3 there, so that doesn't simplify. 24 is 2 and 2 and 2 and 3. So that does have a set of 3. So I can simplify that to 2 times the cube root of 3. And there we go, there's my expression. Okay, so nothing too groundbreaking here. Okay, this guy down here, so we're going to simplify this one. This one's a double distributive property, right? And when we distribute this, I'm going to get 9 minus 3 root 2, and then plus 3 root 2, and then minus the square root of 4. These guys cancel each other out. Square root of 4 is 2. So that's just 9 minus 2, or 7. So this right here, this is an example of our friend's conjugate, right? Okay, so this is a conjugate pair. Okay, we looked at those before when we did imaginary numbers. Conjugate pair, same expressions, different signs in the middle. All right, now this last one here I bring up because this one looks like it's going to be a conjugate pair, right? So when we look at this, right, do my double distributive property, I'm going to get 25 and then minus 5 cube root of 3. And then we're going to get plus 5 cube root of 3. And then I'm going to get minus the cube root of 9. So these guys still cancel each other out, but unfortunately, this isn't a perfect square, right? We're not taking a square root anymore. So even though the 9's a perfect square, it's not a perfect cube. Okay, so these guys are not particularly useful because it doesn't make anything kind of cancel out and make the roots go away. Okay, so just kind of a side note to help you out a little bit. Not particularly useful, all right? So sometimes conjugates are very useful, sometimes not as useful, and that's an instance where they're not.